Good afternoon, everyone. Welcome to Student Revision Tutorials. Today we are going to look at tech active questions for mathematical methods, focusing on trig functions. I am Shelley Cross, and I currently teach mathematical methods at St. Hilda's School. Our learning intentions for today, let's have a look at them. So in today's webinar, we're intending to solve trig equations in a calculator application using numerical solve and a graph application by finding points of intersection of two functions. We'll consider the implications of the parameters a, b, c, and d for the functions y equals a sine x plus d and cos, sketch graphs of the forms listed above, and solve some mathematical modelling questions involving trig functions. Here are our questions for today. Let's get started. I'll keep the questions on the side so you might be able to see them. That way I can see them as well. So today I'm going to be using the TI-Nspire CX Premium Teacher software to solve these questions. I've started a new document in my software and I'm going to begin with the graph page. Our first question, question 1, find all solutions to the equation sine x equals a half for the domain x is an element from 0 to 4 pi. So the way I'm going to approach this question is I'll start by drawing two graphs. The first graph I'm going to draw is the graph of sine x. The second graph I'm going to draw, so I'll split the equation at the equal sign, is the graph of y equals a half. So hit tab. I'm going to enter that function, that graph as a fraction, so control, divide, and 1 down arrow 2, enter. So here I can see my two graphs. The first thing I'm going to do is change the domain because the domain we were looking at is from 0 to 4 pi. So double click on the minimum x value. I'll type 0 and hit enter. I'll move that out the way. Double click on the maximum value and I want the maximum value for x to be 4 pi. So I'll do 4 and I'll use this button at the bottom, the pi button, to put 4 pi in there. Hit enter. Now I don't have to change the values, the values shown for the y-axis, but I do like to tidy that up a bit, so I'll change the maximum y value to 4 and the minimum y value to -4. I can see quite clearly now that the graphs intersect in 4 different places, so there should be 4 solutions for the given domain. To find the points of intersection, we'll go Menu, and I'm going to use the geometry tools here because the geometry points and line tool allows me to find all of the points of intersection at the same time. It asks me to choose the graph, so I'm looking at graph 2 and graph 1 and shows me all of the points of intersection. I'll escape to get rid of that tool. And here are my points of intersection between these two graphs. The points of intersection are the solutions for x. The x value gives me the solution for x. Now all of those values are being given to us in decimal form. The nice thing about the graph view is it shows you how many solutions you can see. Let's do the same thing now using a calculator page and use numerical solve, and we'll see how that gives us some different options. So I'm going to insert a calculator page. On my calculator page, I'm going to use numerical solve. So I'll use Menu, Algebra, Numerical Solve. Type the whole equation as I see it, which is sine x, right arrow to get out of the bracket, equals a half. Again, I'll use the fraction key, 1 down arrow 2. And because I'm solving for x, I must use this comma here and tell the calculator that the variable I'm solving for is x. So comma, x, and enter. Now what the calculator does is it's only able to give me one solution. It gives me the first solution, which if I flip back to the graph page, I can either flip back to the graph page by clicking 1.1. I'll see the first solution was 0.524. I can move between screens by using the values of the pages at the top, the tabs, or Control right arrow takes me back to the other tab. Now this answer is not an exact form. What we can do though to convert the answer to exact form is remove the pi and then turn it into a fraction. So let's divide this solution by pi, approximate this answer to a fraction, so menu, number, approximate to fraction, and I can see that that answer is actually 1/6. So that tells me that the decimal fraction 0.5235 is really the same as pi on 6. In order to find the rest of the solutions, I use the up arrow and enter to copy my equation down. Now I want to find the solution that is the next biggest, so the solution that is bigger than this solution. So I need to put a restriction here using the such that key. Control equals and choose such that, and I want x in this case to be bigger than my first answer. So x, such that x is bigger than, up arrow to my first answer and enter again. So this should correspond to my second value on the graph. Let's have a look. Control, left arrow, my second x value is 0.262. Control, right arrow, sorry, 2.62, there we go, not 0.262. Sorry, 2.62, there we go. Right, so I'll do the same process now, divide by pi to get rid of the pi from the answer. Menu, number, and approximate to fraction. And this answer approximates to 5 pi on 6. So the value of numerical solve is that we can generate our solution in exact form by using this strategy. The value of the graph tells me that there's actually 4 solutions, so I shouldn't really stop yet. I should keep going. So up arrow, copy my equation, get rid of that value because I want the next one, so I need the next biggest value. So I go up and find, I want something bigger than 2.62, so the answer for x bigger than 2.62, and enter, and so on. I don't think I'll continue with those because I'd rather move on to the next question, but I would need to do this 4 times to make sure that I've found all of the possible solutions to that equation. Hope that's all good. So let's look at the second question. For the second question, investigate the effects of the parameters a, b, c, and d for the function y equals a cos bx plus c plus d. I'm going to look at the effects of these parameters using some graphs. So I'd like to insert another graph page. At this point, in order to keep my calculator, my document on my calculator tidy, and particularly in an exam situation, this is an excellent strategy. I'm actually going to insert a problem, another problem. So each question is going to be in a different problem. So when you come back to the end of the exam, when you come to check your questions for question 1, they'll all be in the tabs 1.1, 1.2. Question 2 will now be in the tabs that will start with 2. That's it. It's quick and easy to find what you've done. You haven't deleted things that you might need to look at later, and everything is available for you to check. So I'm going to look at the graph y equals cos x to start. So I'm going to look at the basic function y equals cos x and enter. And I'm going to look at this function for 1 cycle. So I'm going to change my domain, and go from 0 to 2 pi. what I'm really looking to see is what is the effect of these parameters on the shape of the graph. I'll tidy this up as well, and I'll make this maybe 4 and minus 4, so it's nice and easy to see. So here's my original function. The first parameter I'd like to investigate is a, which is the number in front of cos. So let's type in another graph here, and let's use the graph y equals 2 cos x and see what happens. Hit the tab button. I'm now on the second function, so I'm going to simply type 2 cos x, and straight away I can see that the graph has had a dilation in the y direction. So the amplitude of the graph, the original graph had an amplitude of 1, the new graph has an amplitude of 2, so the effect of A is to increase the amplitude or change the amplitude of this graph. The period of the graph between 0 and 2 pi has stayed the same. The graph still completes one cycle within 2 pi radians. If I was to change this graph now, let's add another graph, and let's make the value of A negative. Let's put negative 3 cos x. We would expect this graph to now have a bigger amplitude, so the amplitude should increase, but the effect of the negative is to reflect the graph around the x-axis. So there we have the effect of A on the shape of our graphs. Let's look at B. I'm going to stay in the same graph page. Let's look at the tab so you can see these are all my graphs. I really want to compare everything to my original graph, so I'm going to deactivate the second two graphs. So my original graph y equals cos of x. The value of b is the number in front of x. So let's see what happens when I change that. So I've got cos, let's make the value of b 2. So what happens now is we can see that the effect of b is to change the number of cycles I see within that initial 2 pi domain. So b really tells us, the value of b tells us something about the period of this graph. In the first case, the blue graph, we see one cycle within the 2 pi, but for the second graph, cos 2x, we have 2 cycles within the given domain. Let's look at y equals cos 3x. So we would expect in this case to have 3 cycles within the given domain, and yes, 1, 2, 3 cycles. So I'll deactivate those ones again, and let's go back. Deactivate that one and that one. Back to our original graph, let's look at the effect of C. C is called the phase shift. So C has the effect of translating the graph along the x-axis towards the left or right. Let's see what that looks like. So I'm going to look at the graph cos x, and let's subtract pi on 3. So notice all of these graphs that I'm drawing are in radians, not degrees, which is why I'm using pi. My domain is 0 to 2 pi, not 360. So I've got x minus pi on 3, and my new graph now, my original starting point seems to have shifted a certain number of places to the right. I wonder what that value is there. If I think it's pi on 3, a good idea at this stage is to go into the window and change the window settings and make the window scale pi on 3. Because that'll give us a good view of exactly what's happened. Pi divided by 3. And there we go. So my scale is pi on 3, and I can see the graph has actually shifted pi on 3 places to the right. So the effect of C is to shift the graph to the left or right, the number of places, in that x direction. Right, the next thing I'm going to look at is the value of d. So I'll pop that equation off. Let's look at the graph of y equals cos x, and let's add 2 at the end. Right, so the effect of d is to change the equilibrium position or shift the graph up 2 places. At +2, I can pop in another graph here. Let's just draw the graph y equals 2. We can see the equilibrium position is now 2, so the d value is 2, and the original graph has shifted up 2 places. Right, so that pretty much looks at the values of a, b, c, and d, and the effect they have on the basic cos function. They have exactly the same effect on the sine function. A has a change in the amplitude, which B has a change in the number of cycles across the normal domain. C has the phase shift to the left or right, and D is the vertical shift up or down. Right, let's look at question 3. In question 3, we need to sketch the graph of y equals 2 cos x minus pi on 3 minus 1. So let's have a look at that graph. We're going to insert a new problem, and I'm looking at a graph page. Right, so let's type this graph in. What have I got here? 2 cos, so the 2 suggests straight away that the amplitude is going to be 2, so the maximum height above the mean position is 2, and the maximum depth below the mean position is 2. X minus, that's pi on 3, that's what I did on the previous one. So control divide, let's do pi on 3, right arrow, minus 1. And again, noting the domain is from 0 to 2 pi, so double click on the minimum value and make it 0, enter. Double click on the maximum x value, make it 2 pi, and enter. Right, so here is my graph, y equals 2 cos x minus pi on 3 minus 1. The instruction says sketch the graph, so when I sketch the graph, it's important that I make it clear where on the x and the y axis what the maximum and the minimum values are. I do like to also put in the mean position. So the new mean position is the line minus 1. We don't really need it to be red. So let's just change it. I'm going to right click on it and make it a bit grey. So that's, I quite like to put that line in there because it shows me the symmetry of the graph, and I can see that I have interpreted the vertical shift correctly. The problem here is that the automatic axis doesn't really help me find the value of the x-intercept. So we can do a bit of trial and error, but because this is shifted by pi on 3, let's change the window value and make that window setting. So I went menu, window zoom, window settings. Let's make the scale here equal to pi on 3. Sometimes this works, sometimes it won't work. But pi on 3, pi on 6, pi on 4, often good values to think about changing to. So there we go. I can see that my graph crosses over. That's pi on 3. So 2 pi on 3 is the first x-intercept. 3 pi on 3, 4 pi on 3, 5 pi on 3, 6 pi on 3, which is 2 pi, second x-intercept. Right, question 4. Again, for question 4, I'm going to what am I going to do? Question 4, I'm going to insert another problem. So doc, insert problem, and now I'm in a position to look at question 4. So for question 4, the height h of t meters of the tide above mean sea level during a particular day at the seaway is given by h of t equals 4 sine pi on 6t plus 1, where t is the number of hours after midnight. The first thing I have to do is draw the graph of h of t, for t is an element from 0 to 24, so I'll add a graph page. My graph is 4 sine pi on 6t, so again control divide, pi down arrow 6. Now I'm not using t, I'm using the variable x, so let's put x there, plus 1. Right, so here's my function that I'm looking at. So the height of t is the height of the tide for 0 to 24, so for 24 hours. So my minimum x value is 0, so double click and change that to 0. Our maximum x value is 24, so I can see that the tide has 2 highs and 2 lows. So when was high tide? So I need to find out when that high tide occurred. I'm going to do that using my Analyze Graph tools. So menu, Analyze Graph. I'm finding the maximum value because I want to know when the high tide was. So my first high tide occurred after 3 hours. Menu, Analyze Graph Maximum. And my second high tide occurred after 15 hours. So if the time is measured from midnight, after 15 hours, that would be 3 in the afternoon. So high tide was at 3 a.m. and 3 p.m. Now a boat can only cross the seaway when the tide is at least 3 meters above mean tide level. So 3 meters above mean tide level, well, if the mean tide, let's look at this D value. So the mean tide is the vertical shift. Let's put that in here. So my vertical shift was 1. So this line, the red line, shows me my mean tide level. If I'm looking for 3 meters above mean tide, it means that I'm really looking for let's put in another graph here. I'll get out of there, tab. 3 meters above the mean tide. If the mean tide is 1, 3 meters above that is 4 meters. So I'm really looking for where these two graphs, the black graph and the blue graph, intersect. Let's make this one here grey because really I'm just looking at the mean tide there as an indication of how many units I needed to add on to find 3 meters above. So the boat can cross the seaway when the tide is 3 meters above mean tide level. So I need to find the points of intersection of the black line and the blue line. So again, I'm going to do that using the geometry tools. So menu, geometry, points and lines, intersection points. So I'm looking for the black line and the blue line, and that shows me all of the points where the tide is above 4 meters high. So to answer the question, the boat can only cross the seaway when the tide is 3 meters above mean tide. So between 1.62 and 4.38 hours, the boat could cross the seaway. And from 13.6 hours to 16.4 hours, the boat could cross the seaway. Now that doesn't seem like a very easy time to understand. So maybe we need to now go and look at a calculator page and see if we can put those times into hours and minutes. That would answer the question a little more suitably. So let's insert a calculator page. I'll just look at my graph. So of my graphs that I have here, f of 1 is the graph showing me the height of the tower, f of 3, which is 4. So really I need to solve for when the function f of 1 is equal to 4. So let's do a numerical solve for that. So I've gone Menu, Algebra, Numerical Solve. Now I'm going to look at my variable button. So the variable button here, the function was f1. So f1 of x was my function, and I'm looking to see where is this function equal to 4. And I'm solving, comma, x. 1.619, let's check if that's correct. So it's given me only one solution, or that certainly is the first solution. So 1.61968, in order to convert this into time in hours and minutes, I'm going to subtract 1 to get rid of the hours and multiply the decimal by 60. So that's really 37 minutes. So the first time the boat can cross the seaway is at 1:37 a.m. In order to find the second time the boat can cross the seaway, I'm going to do a similar thing as I did prior. Copy the equation down. Now I want to solve where x is such that x is bigger than my first answer. Which gives me 4.38. Going back to my graph page, 4.38 certainly is my second solution. Again, I will subtract the hours, multiply the decimal by 60 to turn it into minutes, and that means my second time is 4 hours 23, around to 23 minutes, because 0.8 is closer to the next minute. So the boat can cross the seaway between 1:37 a.m. and 4:23 a.m. That's going to help me with question D, part D, because in part D I have to say how many hours in a day can the boat cross the seaway? Well, I can subtract those two times and work out how many hours the boat is going to be able to cross the seaway. Let's go back. Let's first work out the time the boat can cross the seaway between the number of hours the boat can cross the seaway between the first two intersection points here. So we've got 1.62. Let's find that answer. Actually, let's start with this one. 4.38, subtract this one here. So that's 2.76. So how many hours and minutes is that? So subtract 2, multiply by 60, and that gives me 2 hours and 46 minutes. So I've found the first part, or part D. In order to find the amount of time, the times between which the boat can cross the seaway, I'll do exactly the same process on the second 2 points, subtract them, and work out the amount of hours that the boat could cross the seaway for part D. Thank you very much. I hope that's been useful. There will be a worksheet which you'd be welcome to access on the Texas Instruments website, which relates directly to these questions with solutions that will help you if you can't remember any of the information. Thank you very much for being involved in the presentation. I hope that any questions that you've had have been able to be answered. Thank you very much.